Hello everyone and welcome to University Physics 1, Physics 211. And this is going to be the first video for our semester. And as you can see here, we're going to be starting with Chapter 2 material. Chapter 1 discusses unit and unit analysis. And at this point in our college career, we assume that everyone knows how to convert units, feet to meters, kilometers, miles, etc. And if not, there's always Google, or we can look these conversion values up in the appendix of our book. So with Chapter 2, this is the first chapter in the book where we actually start learning about the physics. And at the beginning of every chapter in this book, there is a question that is posed to us. And that question is, what is physics? And then in each chapter, they pick a particular topic which can then be answered using the physics in that chapter. But this is a really good place to start, especially if we've never had any background in physics before. Some of you may have had physics in high school. Some of you may have even had AP physics courses. Some of you may not have been exposed to physics at all, and that's okay. We're gonna start at the very beginning here. So if any of this stuff does look familiar to you, great. Just kind of bear with me as we go through and solidify all the definitions and the mathematics. But eventually we'll get enough groundwork done that we can continue on with the physics that some of you may not have seen. So what is physics? Well, a better question might be to ask, what is the universe? And that might seem like a really complicated question, but the universe is only comprised of two things, arguably. One of those things is going to be matter, and I realize that we could also argue the existence of antimatter and dark matter and those kinds of things, but we'll just clump all of that together into this one category. And then the other category would be energy. And again, there are different kinds of energy, just like there are different kinds of matter. There's a theorized dark matter, which we really don't understand. But for right now, this is an introductory course. We'll go ahead and deal with just these two components of the universe. And when it comes to matter, if you want to study matter and how matter interacts with other forms of matter, then you'll take a chemistry class. If you want to know about energy and how energy can be transferred or transformed between different objects, then you'll take a physics class. And one of the types of energy that we'll really be focused on in this semester is energy that is associated with motion. And so in order for us to really gain some knowledge as to how that energy is related to the motion of the object, we first need to understand how and why objects move the way they do. And for that, we are going to see a combination of the two fields of study paired with mathematics, and then you get everything else. So all the other engineering and science courses out there, all of those are going to be some combination of chemistry and physics tied together with the mathematics. And so if you notice, everyone on campus, regardless of what their degree is, has to take a certain amount of physics and chemistry and math courses. And that provides you with the foundation knowledge that is required to move forward and study really any other field of science, engineering, mathematics, etc. And so we're going to be focused on the physics for this semester, specifically the motion of objects. And then once we have all of the groundwork for motion and the mathematics that describe the motion of the objects, then we can come back and we can start talking about the energy that's associated with those objects and those systems. So first things first, we need a number of definitions. We want to be able to talk about an object that is moving through space, but before we can do that, we first need to know where that object is. So I'm just going to place a little dot on the screen. So there's our object. Eventually that object will start moving around. We'll allow it to move. But for right now, I need to figure out where that object is. And you're looking at your screen right now and you can say, well, it's right there. But if we were to describe in detail to someone who can't see the screen where that dot is, how would we do that? So what we're asking for is, what is the location of this object, or what is its position? And the position is going to be the physical location of the object. But we have to be able to measure that physical location with respect to some predetermined frame of reference. And so we're going to put in here with respect to a frame of reference. So that brings about another definition. What is a frame of reference? So frame of reference. Well, this is going to be start over here. This is going to be a reference frame with a predetermined origin. It's usually not good to use such circular definitions. Here I have frame of reference and I say that it's a reference frame. Well, it makes more sense when we actually draw this out. So if I were to draw a reference frame somewhere on the screen, all I need is some point or location where I want to begin measuring things from. So maybe I choose this point right here. And I'm going to let that be the origin of my reference frame. Then I will draw a number line which extends in both directions. The origin is where we will have the 0 point on our number line. And then traditionally, moving to the right is how we measure our positive direction. Moving to the left of the reference frame is how we measure our negative direction. And the horizontal reference frame that I've drawn here is traditionally labeled as the X reference frame. Now this number line, I can only travel either to the right or to the left. I can't currently travel up or down or into the screen or out of the screen. I can't do the three-dimensional motion yet. We're going to save that for chapter 4. So So right now everything that we're focused on is going to be for one-dimensional motion. So what I have in front of me is a one-dimensional reference frame, and now if I were to measure the location of our point, now I just need to count out along the reference frame until I get to that point. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We are 9 units to the right of the origin of our reference frame. Now when I say units, well, we haven't really decided yet what we're going to be using for the units of position, but we have quite a few options available to us. We could use meters, we could use feet, we could go different sizes of those, like centimeters, inches. We could even go up to things like kilometers or miles, but the standard international unit for measuring length, distance, position is going to be the meter. So I'll go ahead and say that everything on this reference frame is measured in meters, and so every one of those tick marks is a value of 1 meter. So our particle is currently at the location 9 meters. And because we are on the x-axis, or the x reference frame, I'm going to go ahead and say that the value of x for our particle is equal to 9 meters. So now we have our definition of position taken care of. We have our definition of reference frame taken care of. Now that I know where this particle is, now we can finally allow it to move. So I'm going to allow this particle to move, and I will move it all the way back here. I'll move our particle back here to this location. And at that location, we are at the value -2. So we are 2 units to the left of the 0 point. As we move to the left, we become more negative, so that's a value of -2. So we started with a position of +9, but now we have a position of -2 meters. And here's where things are going to get confusing really quick. You'll notice that I've labeled both of these values as x. Well, I can't have this particle existing at 2 locations at the same time. So what we need to do is we need to specify which of these locations did we start at and which location did we end at. And so we're going to expand upon the definition of position. Right here we have what we call the initial position of the object. Initial because this is where we initially started. And we are going to incorporate a subscript of 0. Some books will incorporate a subscript of I for initial, but there are some books that prefer to use the 0. In a lot of computer programming classes or math classes, typically you'll start at 0 in your counting. Also because at some point we may need to start considering what the time values are. And it's always best to start your physics problems at time equals 0. And so that kind of plays into the idea of what we're going to use here. We're going to say the position of our particle when we start the clock at 0 is at 9 meters. Well, then we have, correspondingly, a final position. And we'll go ahead and incorporate a subscript of F for final. And now it's not nearly as confusing because the two values that we have are distinguished between the initial and the final. And because we've moved from one position to another, we've changed position, we call this action a displacement. We have displaced our object from one location to another. And so there's another definition. Displacement. And our definition of displacement is a change in position. So let's take a look at our displacement up on the reference frame here. I started at +9, I ended at -2. And so that displacement requires a total of 11 meters moving to the left. So in other words, I have to move 11 meters in the negative direction. So how can I put this information together? Because that's the next step, is we want to be able to describe what's happening in these systems using mathematics. So how do I combine the initial and final position values in such a way that I produce a -11? So to help us out with that, we're going to come back to the definition of displacement. And all we have right now is change in position. Well, I would like to update this description. Instead of using the word change, I'll use a synonym for the word change. We'll say difference. So displacement is the difference in the position values. But the word difference has a very specific meaning in science and mathematics courses. To take the difference in two values means to take a subtraction. Now I have two values. I have a 9 and a -2. And unfortunately, subtraction is not a commutative expression. I can't just flip around the values and take the subtraction in any manner that I want, because I'm going to get two different outcomes. With the top outcome, I have 9 minus a -2, which makes for a +11. The bottom expression, we have -2 minus 9, and that gives us a -11. Well, that's the value that I want down there, so I guess this means that the order in the subtraction that I have to take has to be from this bottom combination. And what we're going to do is we're going to replace those numbers with the initial final designation. So right here, this was actually the final position value, and we had to subtract from that the initial position value. And this is what gave us the value of our displacement. And this will, in fact, be the definition of displacement, or better yet, the definition of any difference is we have to have final minus initial. Anytime we have a difference. It's going to be final minus initial. And we can shorthand this by using a little triangle, which we call delta. So we have delta x, and delta x is our displacement. That delta will always imply final minus initial. And as we're going to see here, we don't have to limit ourselves just to displacement. We can have any kind of delta statement. We can have delta time, which implies some final time minus some initial time. We could have a delta temperature. So as temperature changes, final temperature minus initial temperature. We could have delta V, change in velocity. Really anything that changes can be described using a delta function, but every one of those deltas has to be final minus initial. So back to our drawing here. Can we in fact duplicate the displacement by taking the difference of these values? And as we've already seen, negative 2 minus 9 does in fact equal negative 11. That's what we wanted up here for our displacement. Okay, let's try going the other direction. And I'll provide us with a fresh diagram here. So our particle is now at the negative 2 position. And let's take it back to the positive 9. To do that, well, now we're going to have to displace in the other direction. As we displace to the right, our values start to become more positive, and just like before, we know that we're going to have to displace 11 units, so this displacement should be positive 11. Can we use this expression to duplicate the value that we're expecting? And the answer is yes. But one very important thing that we need to do here, now that we're going back, we need to remind ourselves of where are we starting and where are we ending. The initial and final position values for this displacement have now switched places. I'm starting at negative 2, I'm ending at positive 9, and so if I take the difference in those values, I do in fact get the proper outcome of positive 11 meters. Alright, so that's our definition of displacement, delta x. Now that we have displaced, I'm going to put a new reference frame up here. Let's go from negative 2 to positive 6 this time. So we're going to start here at negative 2, and we will displace to, oops, sorry, that should be positive 6. And so that displacement, final minus initial, should be positive 8. We have 6 minus negative 2, so that is positive 8. Well, now that we've made this displacement, let's talk about how much time it took for us to do that. And we'll take out our stopwatch, and at our initial position there's going to be some time value associated with that position. Later on, once we get to the final location or the final position, there will be a time associated with that final position. And so just like the displacement, as we showed up here, we can represent a change in time as the difference in the times that correspond to those position values. And as I said, if possible, go ahead and let your initial time be 0 seconds. Because then, if your initial time is 0, then your final time just automatically becomes the time interval delta t. So we take out our stopwatch and we watch this particle as it displaces the 8 meters, and it turns out that it took 2 seconds for this object to move the 8 meters along our reference frame. Okay, that brings us to our next definition. What is the velocity of this object? And velocity is going to be change in position over change in time. Now, we've already dealt with change in position, that is delta x. And we can use the same approach in the definitions for change in time and call that delta t. So what we really have here is x final minus x initial over t final minus t initial. We already know what the difference in the position values is. That was 8 meters. And we've already measured the time interval delta t as 2 seconds. Now here's the really nice thing about this. I said let t initial be 0, and if that's the case, then the final time value has to be 2. So no problem. Delta t is equal to 2. But what if we had something else, like maybe I messed up with my stopwatch and I didn't start measuring until 3 seconds. Well, it's still going to take 2 seconds to get from the initial position to the final position, so we still have a time interval of 2 seconds. The only difference is how that initial and final time value is expressed. Either way, it's 2 seconds. And so either way, we have 2 seconds. 8 divided by 2 makes for 4. The units are going to stick around. And we now have an expression for velocity in meters per second. This object had a velocity of 4 meters per second. So for every second that goes by, this object is going to displace by positive 4 meters. Okay, we notice the displacement came out positive. The time always has to be positive. We are not going to deal with negative time values in this class. If you do find yourself with a negative time, stop what you're doing, go back, check your work. Alright, so there's the velocity. One more definition. Acceleration. Now, we have all been in a car at one point, and we know that the car can displace. We know that that car can have a given velocity. We also know that that car can accelerate. That's why we have the gas pedal and we call it the accelerator. Well, the accelerator or the acceleration is going to cause a change in velocity with respect to a change in time. Well, we're already familiar with the terminology here. We have a change in velocity. So just like in the previous statement, we can take that to say delta V. There has to be some change in velocity. So a final velocity minus an initial velocity. A change in time, well, that's a final time minus an initial time. Well, I would need some values here. So let's take a slightly different approach to this. Instead of using a number line, let's actually jump into a vehicle. Let's say that you're in a truck or a car, and you're at a stoplight, so you should not be moving. So our initial velocity is 0. But then the light turns green, and you're going to accelerate for a certain amount of time until your vehicle reaches a final velocity of 5 meters per second. And we have a friend with a stopwatch that is timing us. And it turns out that it takes about 10 seconds. Oops, got the wrong units in here. 10 seconds for this to happen. So what is the acceleration of the truck? We have our final and initial velocity values. That's going to be 5 minus 0 respectively. And then our time interval, delta t, well, again, it doesn't really matter what the initial and the final values are. What matters is that the total difference between them is 10. So we put all that together, and we get an acceleration of 0.5 meter per second squared. And the reason this has to be meters per second squared, if we look back at the units of the terms that we're using, velocity has units of meters per second, time has units of seconds, and so when we combine those, we get meters per second squared. So we have all these terms, most of which we've heard of at some point or another. So we have x for position in meters. We have delta x for displacement, also in meters. We have v for velocity in meters per second. And we have a for acceleration in meters per second squared. And that delta x can be written out as x final minus x initial. Velocity, as we said, that was delta x over delta t. And I'm just writing all of this out again in a cleaner representation here. Acceleration is change in velocity with respect to time, so that's v final minus v initial, all over t final minus t initial. Okay, so there's everything that we have so far. I want to focus on these two expressions, because now that we have delta t worked in there, remember, delta t is the time interval that everything has taken place with. And I want to consider another real-world situation. Let's say that you are going to drive from Rapid City to Sioux Falls. And I do this problem every semester in class, and I ask everybody, how far is it from Rapid City to Sioux Falls? And almost without fail, people say, oh, it's about 5 hours, 6 hours, 4 hours. All depends on how fast they're driving, right? Well, those are times. They're not displacements. They're not distances. Obviously, the time that it takes you to drive from one location to another is going to vary based on how fast you're driving. But the physical displacement between the two cities is fixed. And just for the sake of this example, I'm going to go ahead and say that this displacement is 350 miles. All right. So we have a displacement of 350 miles, technically to the east, but we'll just go ahead and assume that east is the positive direction. Then we have to consider a time interval. So how long does it take to drive from Rapid to Sioux Falls? And this is where we get a bunch of different answers. You know, some people are speeding the whole way. It might take them 4 hours. Some people might take them 5 hours. Some people, you know, they're hitting all the rest stops and tourist traps along the way, and you know, it takes them even longer. Well, let's say that with everything that was going on, it took you 5 hours to get from Rapid to Sioux Falls. Well, change in position over change in time, that's velocity. So what we have here is 350 miles per 5 hours. That works out to be 70 miles per hour. So that was your velocity. But was that your velocity for the entire trip? And the answer is probably no. Because as I said, there's a lot of things that can happen during this trip. You may find yourself having to travel through a construction zone where you have to slow down. Maybe you have to stop for gas. Maybe you pull over to use the restroom. Maybe there's a speed trap somewhere. And so during your trip, you're constantly going to be speeding up and slowing down. You're not going to achieve a constant 70 miles per hour for the entire trip. This value that we have calculated is what we call the average velocity. And these average velocity terms happen because your time interval is too big. 5 hours, that's a long time. And there's a lot of stuff that can happen in those 5 hours. And so the best that we can do with those large time intervals is to calculate an average velocity. So is it possible to calculate an instantaneous velocity? Is it possible to take one location or one point in time during your trip and measure the velocity there? And the easy answer would be, yeah, I can just look at my speedometer and that'll tell me how fast I'm going. But from a math standpoint, figuring out the instantaneous velocity would require us to take our definition of velocity and shrink our time interval down to an instant in time. And so that brings up the question, well, how long is an instant? And this is where the calculus comes in. So this is why we have our calculus prerequisite. In calculus, we spend quite a bit of time talking about limits and what happens to different mathematical expressions as we take limits that approach certain values. Well, in our case, we are looking at shrinking our time interval down to an instant in time. In other words, delta t may as well equal 0. But we can't let delta t equal 0. If we do, then we're dividing by 0, and that's bad. So instead, what we're going to do is we're going to apply this limit process with the calculus, and we're going to change the notation of our definition for velocity to the differential notation. So the instantaneous change in position with respect to time will give us the instantaneous velocity of the object. And so this is how we distinguish between the two. For average velocity, we actually need to know what the displacement is for a given time interval. But for instantaneous velocity, well, in this case, I would have to have some kind of a function for my changing position with respect to time so that I could take a derivative of it, and that would produce a function for the velocity, which I could then evaluate at any instant in time. So that's how we get our instantaneous velocity. But the two of these are two very different expressions. Again, one happens at an instantaneous moment, the other happens over a very long time interval. And just in case you're wondering how big does a time interval delta t have to be so that we have to call it an average, well, we'll make it easy. We'll just say anything bigger than 0 is too big. And I know that doesn't leave much else, but that will actually ensure that anything other than the instantaneous calculus version of our equation will have to be represented as an average. Now, if that can happen with velocity, what about the acceleration term? Because that's also incorporating a delta t. Well, unfortunately, the same thing is going to have to hold true. Because if you are changing your velocity over a given interval of time, and that time interval is fairly large, hence anything bigger than 0, then the best that you're going to be able to do is to get an average acceleration. If you want to get an instantaneous acceleration, well, then you're going to have to figure out a way of rewriting the expression as a differential. And that would mean having some function of your velocity with respect to time that you can take a derivative with respect to, so that you can get a function for acceleration with respect to time. But, well, we've already seen this before. We've already seen where velocity functions with respect to time come from. They come from the instantaneous velocity expression down below. So we actually have two ways that we can describe the instantaneous acceleration. We have our average acceleration, which is change in velocity over time. Our instantaneous acceleration is dv dt, but where did v come from? Well, v came from dx dt, which means we can actually get the same acceleration by taking the second derivative of our position function. Well, now that we have all of this information, now that we've basically reviewed over how the calculus is going to be applied to these situations, we should actually take a moment, or actually more than a moment, to discuss how we're going to use these relationships of velocity, displacement, acceleration in describing the motion of these objects as they're moving around. So what we have before us right now are three different differential expressions, and what we need to do is we first of all need to figure out how do these things fit together with each other. How does the calculus work? Again, we've all been through calculus 1, but we're going to review the process that Newton came up with for being able to take the derivative of a function. But for right now, I'm going to leave us with this. So we'll go ahead and call this the end of the first video for Chapter 2. And when we pick up on the next video is where we will start analyzing how the calculus is going to affect all of these terms that we've come up with up here. So, see you then.